In this video, we are going to look at the rest of Chapter 2. In Chapter 2, we're going to look at ways to measure the center of quantitative data. A measure of centrality tells us about the center of the values of a quantitative variable. There are many different ways to measure centrality, and you are probably already familiar with some of them. In this section, we're going to look at the mean, the median, and the mode. On page 16 of your notes are the definitions for all three of these. Take a moment and read over these definitions. When you come back, we're going to look at each of these examples for the serial data set. So if you'll recall earlier, we looked at a data set that had 77 different types of serials in the data set. Note that there was a correction made on video 1. In video 1, I had falsely stated that there were 80 types of serial. This was a mistake and has been corrected in your printed notes. So we have 77 different types of serial, and the values of the variable sodium are given on page 17 of your notes. We're going to look at how to calculate the mean, the median, and the mode all by hand. So to calculate the mean, what you want to do is add up all of the numbers in the table together. Adding up all of the numbers, you should find that the total is 12,295. We're going to divide that by the total number of serials, which is 77, to give us the mean. Now notice here that I'm using the notation X bar. That's because this is a sample of 77 types of serial. If we had had population data, we would use the symbol mu instead. Next, we're going to look at how to calculate the median. To calculate the median, the first thing we do is arrange the data from smallest to largest. So notice here in the table we have the data arranged from smallest to largest. Next, we find the middle number of the arranged data. In this case, there is an odd number of data points, and the middle number is 180. Therefore, the median is 180. To find the mode, we're looking again at the data in order, and we want to see which number appears the most. Here, we see the number that appears the most is 0. Therefore, the mode is 0. Take a moment and calculate the mean, the median, and the mode of the following test scores. Round if necessary to the nearest tenth. Pause the video, and when you come back, we'll go over the answers together. For the mean, you want to add up all of the test scores and divide by the total number of test scores. There are 8 test scores in this data set, so we divide by 8, giving a mean of 79.25. To find the median, we're going to write the numbers from largest to from smallest to largest. Notice that the middle two numbers in this case are 79 and 86. Therefore, we take the average of them to find that the median is 82.5. To find the mode, notice that the numbers 74 and 86 both occur twice and are the most commonly occurring numbers. So the mode in this case is both 74 and 86. So the question is, which measure of centrality should you use? Notice that the mode in the sodium example was 0, which does not give us a good idea of where the center of the data set is. The mode only tells us the most common value of the variable. For this reason, the two most common measures of centrality are the mean and the median. One advantage the mode does have is that we could use it with categorical data. The choice of whether to use the mean or the median depends on if the dataset contains outliers. So again, recall that outliers are data points which are very large or small compared to the other data points. They are extreme data points. One way to detect outliers is to look at a plot and see if any of the points look extreme compared to the others or for large gaps in the values. Again, later we're going to look at a numerical way to detect outliers. When a data set contains outliers or has non-trivial skewness, in other words, is sharply skewed right or left, the median is typically used as a measure of centrality. When it does not contain outliers and is roughly symmetric, then the mean is typically used. So let's look at an example. Take a moment and read the example that involves 10 people sitting at a coffee shop. When you come back, we'll have you try an example on your own. Now that you've read the example in the notes, try this example on your own. Think about it for a moment, and then when you come back, we'll talk about the answer. So notice for this example, the teacher is most likely quite a bit taller than all of the kindergartens. Therefore, the teacher's height is an outlier. When we add an outlier to the data set, the mean height will change more than the median height. In section 2.4, we're going to look at measuring the variability of quantitative data. Just looking at the central value of a variable is not enough to fully describe the variable. We also need to talk about how spread apart the values are. Just like there are different ways to describe the center of a data set, there are different ways to describe the spread of a data set. Take a moment and read the definitions of range, standard deviation, and variance on page 19 of your notes. Don't be afraid of the formula for standard deviation. We're going to work through an example step by step. We're going to again visit the variable sodium from the cereal data set. Notice again that there are 77 different cereal types in the data set, which tells us there are 77 different types of cereal in the sample, and that n is equal to 77. The values of the variable sodium again are given on page 17, arranged from smallest to largest. To find the range, you want to take the largest value minus the smallest. So in this case, 320 minus 0 gives a range of 320. Next, we're going to look at step by step how to calculate the standard deviation by hand. And even though the formula looks complicated, we can use a table to help us simplify the calculations. So to perform this example, suppose that we have the following data set on the weight of apples in grams. Before continuing on the example, make sure to read the first part of page 20 in your notes to give an overview of how we're going to calculate the standard deviation. Continuing this example, notice that there are 6 numbers in the set. Therefore, n is equal to 6, and we need to start by calculating the mean. Summing up all the numbers and dividing by 6 gives us a mean of 63.6. Now we can start to fill in the table on page 20 in your notes. We're going to start in the left-hand column by just listing all of the data points. So xi's are all of the different weights of the apples. So notice we've just copied those down. In the second column, we're going to take each of the values on the left and subtract the mean that we just found. So notice, for example, we take 56 minus the mean gives us 7.3. So I paused the video and made a quick correction. If we take 56 minus 63.3, that should be negative 7.3. So again, we're taking each observation and we're subtracting off the mean. For the third column, we're going to take whichever number we found here and we're going to square that number. And so notice here are each of the numbers squared. And again, we really should have a negative in here, so let me add those in. But notice that it's not going to make any difference in the calculations. There we go. And so now this should match the table that you have in your notes. To get expression 1, what we're going to do is we're going to sum all of the values in the third column. And so notice in your notes this gives 1,673.34. Now remembering that n is equal to 6, we can now compute the standard deviation. We take the sum of the third column and divide by n minus 1. And this gives us a standard deviation of 18.2939. To get the variance, we just have to square that value. Students in a class were asked how many children is ideal for a family. The results for males and females are listed below. Calculate each standard deviation by hand and then answer the questions at the bottom of the page. So notice you have a data set for men and you have a data set for women. Pause the video here. Fill out the table for men and the table for women, and then once you have the tables filled out, go ahead and calculate the standard deviation for each, and then we'll look at the answers together. We're going to look at the table for men first. So when you fill out the table for men, these are the values you should have. So notice we started out by writing down the data set. If you take the average of this data set, or the mean, you should find that the mean is equal to 2. So in this column, we've taken each data point minus 2. And then to get the third column, we have squared all of these values. Now to find the standard deviation, what we'll want to do is sum up this third column, and if you add those numbers together, you will get 24. And then, since there are 7 data points in the data set, we're going to divide that by 6. So notice here we find a standard deviation equal to 2. Now, let's look at the data set for women. For women, you should have this table. Again, we've taken and written down all the values of the data set. If you find the average of these numbers, you'll find that the mean is 2. So notice that men and women both have the same mean in this case. Next, for each data set, subtract off the mean. And then to get the third column, square the value that we found in the second. If you add up those numbers, you'll find that they add up to 8. And then again, we're going to divide by n minus 1, giving a standard deviation of 1.156. Now that you've found each of those standard deviations, take a moment and answer these 3 questions. When you come back to the video, we'll talk about the answers together. The first question asks, which gender has more variability? Notice that the standard deviation for men was higher than the standard deviation for women. Therefore, men have more variability. Also, if we look at the actual data set for men, notice that we see more of a variety of numbers than we did for women, where most of the values were equal to 2. So it makes sense to think that men have more variability. 2. Why is the range not helpful here? Well, notice that for both men and women, they both have the same value of range. For both men and women, the range is equal to 4. 3. Why is this a good illustration of why measure of central is not enough to describe the distribution? If we had only used the mean to describe the 2 different data sets, notice both men and women had a mean of 2. So if we use the mean by itself, we wouldn't see the differences between the data sets. On the top of page 23, it says, do I always have to calculate these values by hand? And the answer is no. There are many other ways to calculate these, and they are listed there on the page. So why is standard deviation important? The standard deviation gives us a rough estimate of the typical distance of data values from the mean. The more spread out the data is, the more variability there is in the data. The larger the standard deviation will be. Comparing these 2 plots, we can see that the top data set will have values that are close together, in other words, smaller standard deviation, and the bottom will have values that are further apart, i.e. large standard deviation. Notice that each of these data sets are centered at the value 0. So they have the same center, but very different standard deviations. In addition to calculating the standard deviation, it's important to know some of its properties. The standard deviation measures the spread from the mean of the data set and should be used only when the mean is the measure of centrality. S is equal to 0 when all the observations have the same value and there is no spread. Otherwise, it will be strictly positive. S is sensitive to outliers because the formula for standard deviation depends on the mean, which is also sensitive to outliers. And S has the same units of measurement as the original observations. If a distribution is unimodal and approximately symmetric with a bell shape, then the value of the standard deviation coupled with the mean can help us form an interval containing certain percentages of the data. And so we're going to talk about what is known as the empirical rule. And so here is a picture of the empirical rule to go along with the definition on page 23. What this is saying is if you have bell-shaped data and you know its mean and its standard deviation. So here we're using mu to denote the mean and sigma to denote the standard deviation. So notice if we are within one standard deviation on either side of the mean, that will capture 68% of this curve. If we go within two standard deviations of the mean, we'll capture 95%, and if we go within two, we'll capture 99.7. We could also break down those sections like this. So notice here, 34 and 34 give us the middle 68. We could also break down using those percentages these smaller pieces. So for example, if we know from 2 to 2 is 95%, and this middle piece is 68, then we should have 13.5 in each of these pieces. Take a moment and compare the two images on the page 24 of your notes and make sure that you can confirm the breakdown of this image. So how could we use this? IQ scores are distributed normally with a mean of 100 and standard deviation of 10. What is the probability that a randomly selected person has an IQ between 90 and 110? We can use the empirical rule to help us answer questions like this. To do so, we start by drawing a normal curve. And a normal curve is another word for a bell-shaped curve. And what we're going to do is we're going to start by drawing this and labeling the x-axis. Well, we know that the mean is 100, so we're going to write 100 down at the bottom. And then, since our standard deviation is equal to 10, each time we go up one standard deviation, we're going to add 10 to the value. So 100 plus 10 is 110. If we add another 10, we get 120, and another one we get 130. To the left-hand side, we're going to do the same thing, except we're going to subtract off 10. 100, 90, 80, and then 70 for this last piece right here. So really, we could move this over a little so it's closer to the line. All right. Let's see if we can make this look a little bit closer to that line. There we go. All right. So next, what we're going to do is shade in the area representing the probability that a randomly selected person has an IQ between 90 and 110. In other words, we're going to shade the area under the curve between those two values. And if we do so, we get this image. Notice that we've shaded the area from one standard deviation below the mean up to one standard deviation above the mean. Applying the empirical rule tells us that the shaded area is 68%. Therefore, the probability that a person has an IQ between 90 and 110 is equal to 68%, or 0.68. Let's look at another example. IQ scores are distributed normally with a mean of 100 and standard deviation of 10. What is the probability that a randomly selected person has an IQ between 80 and 100? Again, we're going to start by drawing that normal curve and labeling our x-axis, the same that we did before. Now, we're going to shade in the area representing the probability that a randomly selected person has an IQ between 80 and 100. So notice here is 80 and here is 100. So here is that shaded region. Now we're going to use that plot on the bottom of page 24, and we find that the probability that a person has an IQ between 80 and 100 is equal to 0.34 plus 0.135. And again, we get these values looking at that plot on page 24. Adding those together, we find that we get 0.475 or 47.5%. In this section, we're going to look at using measures of position to describe variability. As we saw previously, just looking at the central value of a variable is not enough to fully describe it. we also need to talk about how spread apart the values are. Just like there are different ways to describe the center of a data set, there are different ways to describe the spread of a data set. So take a moment on page 27 of your notes and read through the different definitions there. Also, read how to find the quartiles. And when you come back, we'll look at an example. So let's look at the 5-number summary. Again, we're going to look at the variable sodium in the cereal data set. First, notice there are 77 different types of cereal in the data set, and this tells us that there are 77 types of cereal in the sample, and that N is equal to 77. The values of the variable sodium are given below, and they're arranged from smallest to largest. We're going to start out by finding Q2. Well, recall that Q2 is the same as the median, and we already found the median for this data set. We found that the median was equal to 180, therefore Q2 is equal to 180. Next, we're going to find Q1. To find Q1, we want to find the median of the first half of the data set when the data is arranged from smallest to largest. Highlighted in green is the first half of the data set, excluding the median, since N is odd. To find Q1, we now find the middle of these values shaded in green. Notice that the middle occurs between 125 and 130. Therefore, Q1 is equal to 127.5. This tells us that 25% of the data falls below 127.5. Alternatively, we could say that 75% of the data falls above 127.5. Pause the video here and see if you can find Q3. You should find that Q3 is equal to 215. Using this information, we can now list out the 5-number summary. The 5-number summary consists of the minimum, Q1, Q2, Q3, and the maximum. Looking at our data set, we could highlight the 5-number summary. And so notice here the 5-number summary is giving us an idea of where all the different values are. We see the maximum, we see what values define the first 25% of the data, the second 25% or the 50th percent, 75% of the data is below these points, and then 100% of the data is below the maximum. Take a moment and for the following 2 data sets, find Q1, Q2, and Q3. Pause the video, and when you come back, we'll look at the solutions. For the first data set, here are the values in order. Notice here that the median is 27, so Q2 is 27. Also, the minimum is 7 and the maximum is 82. To find Q1, we look at the 2 values below the median. Taking the average of those, we find that Q1 is 10. To find Q3, we look at the 2 numbers above the median. Taking the average, we find 60.5. Looking at the second data set, here are the numbers in order. Notice that our minimum is 3 and our maximum is 29. 15 and 19 are both in the middle, so Q2, or our median, is equal to 17. Looking at the 3 numbers below the median, we find that Q1 is equal to 7. And looking at the 3 numbers above the median, we find that Q3 is equal to 28. Next, we're going to look at box plots. Box plots give us a way to visualize the quartiles of the data. They can help us spot outliers. Vertical lines are drawn at Q1, Q2, and Q3 with a box formed around them. The box represents 50% of the data. Horizontal lines are also drawn out from the box to the largest and smallest non-outliers, and outliers are denoted with a dot or other small symbol. Watch the video in the notes for an informative example of box plots and quartiles. Take a moment and read the example on page 30 of your notes. Also, on pages 31 through 32 is an additional example for you to read on your own, where we go through step by step how to build a box plot. We can compare the information in box plots to the information given in a histogram. A box plot does not portray certain features of a distribution, such as distinct mounds and possible gaps, as well as a histogram does. However, box plots are useful for identifying potential outliers, since those outliers are given by a dot. Since technology is readily available, creating both can give you a good view of the distribution. For example, compare the box plot and histogram for the waiting times between eruptions of the Old Faithful Geyser in Yellowstone National Park. This example is discussed more in your textbook. Also, read the example in your notes in your textbook comparing the box plot and histogram when comparing two groups side by side. Next, we're going to look at what a z-score is. A z-score is another tool we can use to help identify potential outliers. The empirical rule tells us that it is unusual for an observation to fall more than 3 standard deviations from the mean. We can use this fact to identify potential outliers. An observation in a bell-shaped distribution is regarded as a potential outlier if it falls more than 3 standard deviations from the mean. For an observed value of a variable x, the corresponding value of the standardized variable z is called a z-score. Z-scores are useful because they put variables on a common scale. On the bottom of page 33 of your notes are some properties of z-scores. So let's look at an example together. The manager of a restaurant records each day for a year the amount of money received from sales of food that day. Using software, he finds a bell-shaped histogram with a mean of 1,165 and a standard deviation of 220. On Monday, sales were 615. Is this an unusually bad day? Justify your answer. Well, to figure out if this is an unusually bad day, we're going to calculate the z-score for the sale value of 615. To do so, 615 is our x, and then we want to substitute in the mean and the standard deviation given in the problem. This gives us a z-score of -2.5. Well, by our rules, the empirical rule tells us that it's unusual for an observation to fall more than 3 standard deviations away from the mean. This value is only 2.5 standard deviations below the mean. Therefore, this is not unusual. On Tuesdays, the sales were $2,000. Is this an unusually good day? Justify your answer. Again, we're going to calculate the z-score for 2,000. In doing so, we find that the z-score is 3.8. Well, 3.8 is larger than 3, so this was an unusually good day. Looking at another example, we can use z-scores to help us compare values for different variables. An incoming freshman at EKU took the placement exam in Spanish and mathematics. In Spanish, she scored an 82 and in math an 80. The overall results of the Spanish exam had a mean of 72 and a standard deviation of 112, while the mean of the math exam was 68 with a standard deviation of 8. On which exam did Julie do better compared to the other freshmen? Read the rest of the example on page 34 of your notes to see how we can use z-scores to compare the two exams. The last section of your book, section 2.6, looks at recognizing and avoiding misuses of graphical summaries. As an introduction to this topic, read the chapter in your book on pages 76 through 80. This video concludes the video to accompany Chapter 2 notes.